All right, welcome back after the long weekend. It's time to talk about a brand new chapter, systems of equations. So we're going to start off today by talking about graphing systems. So as we discussed in our previous graphs, when we did them last chapter, it's really important that whenever we're dealing with a graph, we extend it, make it look as long as possible, because while it's important to be able to draw graphs, it's equally important to recognize that multiple graphs at the same time can serve a purpose for us. So we're going to be talking about linear equations for now, ones which have an x and a y in every single equation. As I've mentioned here, two exceptions are our vertical lines, which are x equals a number, or our horizontal lines, which are y equals a number. So I'm starting off here with a graph of y equals 2/3 x minus 4. Starts at minus 4 on the y-axis, goes up 2 and over 3. I'm also drawing one in point slope form. So I'm starting at -3, -6, and from there I have a slope of down 1 over 2 repeatedly. So when I draw my graphs from edge to edge, I notice that they do in fact intersect. And where they intersect, that is the solution to the system. So that's the only point on the entire grid which is on both lines. Now, we call it a solution to the system because if I was to plug it into each equation would make a true statement, and that's what a solution actually is. I also noted that this is an intersection. That's where two lines cross one another, rather than an interception, where a single line crosses an x-axis or a y-axis. So the notes that I've written here pretty much explain the same thing that I've just been talking about. Let's look at another idea behind this. So this is going to be the case for any linear system, which is what we're working with in grade 10. It is important that you're able to recognize a linear from a nonlinear equation. We've already talked about how if you have a table of values, you can recognize a linear equation because both the x's and the y's go up by an arithmetic sequence. Another way that you can recognize it is by looking at the x exponent and the y exponent. As long as both of these exponents are an exponent of 1, that makes it a linear equation. But if the exponent is anything else, or I see any other type of a symbol, such as a square root or a square or a cube, these are not linear equations. In fact, for these ones, the first is a square root curve, the second is a parabolic curve, and the third is a cubic curve. Let's look at another example. So we're going to solve the system. We're doing it by graphing, and as we get through this entire chapter, there's actually 3 different methods to do it, and you will be responsible for all 3. So for these two, I'm starting out with one of them in slope-intercept form. Starts at -6, has a slope of up 2 over 1. And the other one I've got in general form, which I'm going to rearrange to slope-intercept form because I didn't give instructions saying I had to do it by x and y intercepts. So this one starts at -4, has a slope of up 3 over 2, etc. And I'm working really hard here to make my answer as accurate as possible. You have to be very careful that you're drawing your lines very straight and a thin line, a neat line. We can also use this for word problems. So I've got a jar of nickels, which are 5 cents each, and dimes, which are 10 cents each. I know there are 4 more of the dimes than there are the nickels. Setting up this equation can be quite tricky for us, so you do have to be careful with this. And the jar contains a total of $1.45. We're going to solve for this graphically. So first, the equations. The fact that there are 4 more dimes than nickels means I would have to add 4 to the number of nickels to obtain the number of dimes. So that's where my first equation is d equals n plus 4, even though many of us would immediately write down d plus 4, which is actually incorrect. The other one, I wrote 10 times the D's plus 5 times the N's equals 145 because D's are worth 10 cents and N's are worth 5 cents. I've rearranged that equation so it's also in slope-intercept form, and unfortunately I'm working off my graph here a little bit, so you'll just have to kind of trust me on this one. I'm starting at 14.5, I'm going down 1 over 2. And for the other one, I'm starting at 4, I'm going up 1 over 1. And when I set it up accurately, I find that, in fact, they cross at a perfect number, which makes sense. You can only have a whole number of dimes or nickels. You can't have parts of them. So my answer there was 7 nickels and 4 dimes. Our homework, we've got 2 different pages I'm asking you to work on. Everything I'm asking you to do by graphing. Have some fun with it. I'll see you in the Zoom on our upcoming Wednesday meeting.